Hey, hello. What do you think? Yes, oil and water. Maybe you see a bug in there too. I don't know how that got in there. Yes, polar versus non-polar. So of course you know that oil is non-polar, water's polar. So we need to understand how to identify whether a molecule is polar or non-polar, so we can tell how they interact with each other, if they're attracted to each other or not. In this case, water molecules attract to each other, and they just are pushing oil out of their way. And in this case, oil goes to the surface because it's less dense. But water molecules have a really strong attraction for each other because they're polar, and not only, but also because they interact. There's an attractive force called hydrogen bonding. So that's where we need to go. So let's look at some examples. Thought we'd look at HF first, hydrofluoric acid. Let's draw the Lewis dot structure. So the Lewis dot structure looks like this. Okay. We have a covalent bond there, okay? So what do we know about fluorine? Well, fluorine is the most electronegative element. What's that mean? Fluorine has the ability, because it's very small and has 9 protons, to attract electrons. So this pair of electrons is attracted to this fluorine. So if you think about electrons in orbitals, these electrons are spending most of their time closer to fluorine. Okay, so what does that leave hydrogen with? Well, that just leaves hydrogen with a proton, one proton, and maybe just a partial negative charge. So we say that this hydrogen is partially positive. And this, instead of having just 9 protons, 9 electrons, it has 9 protons and maybe a little bit more than 9 electrons. We say this is partially negative. That's a Greek letter delta. Means partial. That's a small case delta. A capital delta is the triangle. That's a small case delta. Partial negative. So this molecule is polar. It has a positive side and a negative side. Another way to show this is to draw what's called a dipole. So a dipole. This is a dipole, just an arrow. The little tail here, it's called a dipole. We draw dipoles toward the more electronegative element. Toward the more electronegative element. Okay, how do we know what element's more electronegative than another element? Well, the closer you get to fluorine, the more electronegative it is. So we'll look at some examples and we'll be able to figure that out. A dipole. Let's look at water. We know water is polar. So let's look at the Lewis dot structure. Looks like this. Let me draw it like this. Okay, so we have 2 covalent bonds here. Let's draw a dipole for each covalent bond. So, which one's more electronegative? Oh, well, oxygen's right here. Oxygen's right next to fluorine. So it's pretty electronegative. And hydrogen's way over here. So we would draw the dipole toward the oxygen. We draw a dipole for each bond. This is partially positive. That's partially negative. Partially positive. So this molecule is absolutely polar. Notice that the tail of the arrow, the tail of the dipole, is going to be the partially positive side. And the tip of the arrow is going to be the partially negative side. And if you look at that little plus sign there, that might help you remember that. We draw the dipole toward the more electronegative element. The element that pulls electrons closer to itself. All right, let's look at carbon dioxide. Sorry about this, I'm getting a little congested. Let me draw carbon dioxide like this. Just erase this. So carbon dioxide has looks like this. Carbon dioxide. Yeah? Okay, so let's draw a dipole for each bond. Now, which one's more electronegative, carbon or oxygen? So we have oxygen right here, nitrogen, then carbon. So oxygen's more electronegative. We'll draw a dipole like this. Draw a dipole like this. This is partially negative. That's partially negative. The atom in the center, we don't show its polarity because it's not going to have a chance to bump into anything. So, what we can say about this molecule is it's nonpolar because it doesn't have, okay, this is important, it doesn't have something on the outside that's positive and something on the outside that's negative. It only has things on the outside that are negative. Makes it nonpolar, okay? You can also think of, this isn't really correct, but you can think of these, like, these dipoles being representing ropes, and there's a tug of war, and this person's pulling with the same force this person's with, and so they're canceling each other out. I don't really like that much. I like the fact that there's nothing on the outside that's positive, only negative stuff. Makes it nonpolar. All right, let's look at this guy down here. I hope you can see this. H2CO, sort of formaldehyde. Let me draw a Lewis dot structure. Looks like this. Okay. Is that polar or nonpolar? Well, let's draw some dipoles. So we can draw a dipole here. Dipole here. Again, we go toward the oxygen. Hydrogen, you see that little positive sign? It's going to be partially positive. Hydrogens are always partially positive, except for the molecule where it doesn't have a charge at all. At least not a permanent charge. So let's go back to this molecule. This is partially positive. This is partially negative. Okay, so is this molecule polar or nonpolar? Is there something on the outside that's negative? Yes. Is there something on the outside that's positive? Absolutely. So this is a polar molecule. Polar molecules would dissolve really well in which of these layers? Yeah, polar molecules dissolve in water. Nonpolar molecules would dissolve really well in the oil. Let's look at one more, and that's carbon tetrafluoride. Carbon tetrafluoride is tetrahedral. So let me draw like a little 3D sketch of this. All right, and all right, let's draw the dipole. So what's more electronegative, hydrogen or carbon? Carbon is. So all these dipoles would be going toward the center. All the dipoles would be going, gets a little messy. And what's the charge on the outside? Well, it's all partially positive. All right? That central atom, that carbon, is surrounded by hydrogen. It's not going to interact with anything. That's nonpolar. Now notice these two here. Like, this is nonpolar, that's nonpolar, that's nonpolar. You know what they have in common? They're symmetrical, right? So if a molecule is symmetrical about all the axes, then it's going to be nonpolar as well. Polarity. We draw dipoles toward the more electronegative element. Fluorine is the most electronegative element. That's partially negative. That's Greek letter delta. Small case delta means partial, or so that's partially negative, partially positive. And so hopefully you understand polarity. I'll be sending you a worksheet that I'll want you to do for Friday. All right, bye.